What's up, guys? Welcome to another video brought to you by The Simple Engineer. Today we are going to continue the theory of computation, and we are going to be proving the closure of union and concatenation for deterministic finite automatas. So to reiterate what closure is, it's the collection of objects are going to be closed if applying the operation to the members of the collection returns an object that is still in the collection. So what this means is, today we want to prove that two languages A and B are closed under the regular operations. So if I have a regular language A and a regular language B, totally independent of each other, but I apply the union of these two languages. So I say A union B. I want to ensure that the output of this is also regular. And what that means is, I want to ensure that if I union two DFAs, an A and a B, that the output DFA is also going to be possible, is also going to be regular. Because we know that if we have a DFA, there is some regular language that it accepts. Likewise, if there is a regular language, there is a DFA that you can build to accept that language. But if we apply union to these two languages, we want to make sure that there's still a DFA possible if we do so. The same thing with concatenation. If we concatenate a language A that's regular with a language B that's regular, we want to prove that the concatenation of such is also regular. So that's what we're going to be doing today. So this is going to be very proofy. There's going to be quite a bit of math involved, but it's necessary to understand the underlying fundamentals of proofs to really build up the conceptual things that we'll be doing later on. And I'm hoping in this video we will get to some examples on top of the proof to also help your brain kind of understand what this means. So to begin, we have some language that's regular A1, and we have another language A2. These are both regular. So what we're proving, what we want to prove is that A1 union A2 is also regular. So this is what we're going to be doing. So in order to do this, we're going to be using something called proof by construction, where we actually construct a DFA that will be recognized by this language. Because we know that a language is regular, if and only if it can be recognized by some DFA, then this is a very feasible thing to do. So what the union says, we did some examples before, but in terms of DFA, what the union says is union says a language accepts if the input is in the final state of A1 or A2. So if we have a DFA, and this is A1, and we have a DFA and this is A2, and we feed in some string, say 0, 1, 2, 3, if it's accepted by A1 or it's accepted by A2, then it is a valid DFA for union. That's what this means. So we want to prove that this is true. So what we need to do is we must construct a DFA M from the two languages. So we need to construct a DFA M from these two DFAs, right? But the problem is that we're only going to be able to read one input at a time. We can't take a DFA and then read in one and say, oh, it's not accepted. Let's go here and say, okay, is this accepted? You can't rewind in a DFA, right? You can't say, okay, I'm going to read in one here. Oh, it didn't work, so let me just jump over here. What you have to do, the real end goal, is to simulate reading in character input simultaneously to determine if either DFA M1 here, it says A1. So if DFA A1 accepts a string or DFA A2 accepts a string, we're going to be checking that input simultaneously. That's the goal. So the trick, and we'll look at this formally, but the trick is the DFA M, this DFA here, it needs to remember a pair of states. So to get the pairs, you need to take the K1 states from A1. So you need to take all the states from A1, and you need to take all the states from A2, we'll call it K2, right? And you need to cross product them. So K1 cross K2 will get you all the possible combinations of states between the two DFAs. So if we look at this, if we say this is 1, 2, 3, 4, 5, if we were to cross product this, what would this look like? Okay, well if we have 1, 2, and we have 3, 4, 5, we know that the cross product would be, we would have 1, 3, we would have 1, 4, and we would have 1, 5. We would have 2, 3. We would have 2, 4, and we would have 2, 5. And as you can see, you're starting to see the idea, right? We're cross product. So if you haven't seen cross product before, this is what it is. We're taking all the possible combinations of states between these two DFAs. So these would be all the new states in the DFA M, right? So it allows us to track input for all these states. And this is what the DFA would be able to recognize. So now what I want to do is I want to formally prove this, right? So this is the construction. This is basically the idea that we need to approach for proving this idea. So that's exactly what we're going to do, okay? So formally what we would say is we have M1, which is that initial A1 that we were talking about. So there's a DFA M1. So I'm actually going to say that. There's a DFA M1 that recognizes the language A1 where M1 is a DFA. And we know that a DFA is represented by a Q, which is the set of states, sigma, which is the alphabet, a transition function, a start state, and a final state. But because we're unioning two DFAs, we're going to have a second DFA. We're going to say there's a DFA M2. And that M2 recognizes a language A2, where M2 is a DFA. And we'll say that there's a set of states in M2. So we'll call this Q2. We'll keep the alphabet the same. So they'll share the same alphabet, say 0 or 1. That's the alphabet that we'll use. But they're going to have a different set of states. They're going to have different transition functions, maybe a different start state, and probably a different final state, right? So what we need to do is we're going to make like this root parent DFA, like what we said before. And this is going to be denoted by M. We're going to have this parent M DFA. So we make a root parent DFA, say M, where M recognizes A1 union A2. And we'll say where M equals Q sigma delta Q0F. Okay, so this is the parent DFA that recognizes the union of these two above. So this is how we're going to start it. So to make this easy, what we need to do is we need to break down these 5 components within this parent DFA. So Q is the set of states, right? And we know the set of states is the combination of A1 and A2, which is what we did previously. We took the cross product and found all the possible combinations, right? So mathematically, the way that we're going to represent that is we're going to say, okay, for this M here, we're going to say Q equals the set. And the set contains this pair of states that we need to track, right? Which is what we're tracking simultaneously, where R1 exists in the set of states for this M1 DFA, and R2 exists in the set of states for this M2 DFA, right? So it's saying all the states that exist in this new DFA M are going to be the combination of states from M1 and M2. So that's like what we were saying here. We have a DFA M1 and we have a DFA, say, M2. This is just going to be the combination of all 5 of these states. So these 5 states make up all the states in M. Okay, so that's what our Q is. Okay, so this ensures that the states in the DFA M contain all the same states from each of the DFAs that we're unioning. So now we have sigma. Well, we made it easy. The sigma is the same. It's 0, 1. So we're just, or hypothetically speaking, it's whatever sigma is we use in this example. Since this is a general example, we're just saying that the sigmas are the same. If they were different, which they can very well be different, then what we would do is we would just have sigma equals sigma 1 union sigma 2, which would allow you to take input from either or, right? But basically, we're recognizing the input alphabet. They share the same input alphabet. Okay, so next we look at the delta function, which is the transition function. So the transition function states that for each R1 and R2, there exists a state, right, where A exists in sigma, and there's a way to jump from transition to transition. So this is definitely the weirdest one mathematically to represent. But we're going to say that delta, there's a delta that goes from one state on an input, which is going to yield transition function R1 on A and transition 2 for R2 on A. Okay, so I want to basically reiterate that for each R1 and R2 that exists in Q and A that exists in sigma. Okay, so easily what this means is that M is going to take in an input symbol. So M, this DFA reads in some input symbol, A, right? And it's from this state here. Remember, this is R1 comma R2 because the states are represented as pairs. So this would be like R1, R2, and this would be going to like R2, R3. So this is a state right here. It's going to take in some input symbol A. And what this means is it gets a state from M, which is a pair of states. So the output is just another state here. That's what this means. So it looks confusing, but that's how we're representing the transition from state to state. So next, we're going to look at Q0. Q0 is the start state. Okay, well, the start state is going to be the pair Q1, Q2, right? So these are going to be the two start states here. So we have Q1 and we have Q2 here. So it's basically going to be the pair of the two start states from the DFAs that we are performing the union operation on. And that's how we want to think of that. And last but not least, we have the final states. And something to note is the final states are going to be the pairs or the set of accepting states that are accepted in either M1 or M2. So if we had DFA, say in this example, this was accepting and then these two were accepting, and this was 1, 2, 3, 4, 5, then the final states would basically be anything that contains state 2, 4, or 5. So that's what you want to think. It's the set of pairs in which either member in the pair was accepting by M1 or M2. That's how you want to think of that. So the way that we write this mathematically is, and I'll actually erase this to give myself some more room, but we'll say f equals the set R1, comma, R2, where R1 exists in F1 and R2 exists in F2. Okay, so these are going to be all the final states from M1 and M2, and this is how we're mathematically going to represent that. So with these ideas in mind, what I really want to do is I want to show you guys some examples of unioning two DFAs. Performing the union operation on two DFAs. So what we just did is, this is basically the proof for the union of two DFAs. Now I want to show you the application of this, how we would go about doing it. So what I'm going to do is I'm going to construct, similarly to what I was saying, a DFA A1. And A1 is going to be a very basic DFA. We'll call this state Q0, and we'll call this state Q1. And this is going to be our start state. And we're going to loop back on 0, go to Q1 on 1, Q1 goes back to Q0 on 1, and Q1 loops back to itself on 0. Similarly, we're going to have an A2. We'll call this state P0. It's going to be a start state. It's going to take in a 1, loop back to itself, and it's going to output to a P1 on a 0, back on a 0, and then we'll loop back on a 1. So they look similar, but they're very different. The final states are different. The transitions are different, which would be the delta functions. So what we want to do is we want to perform the union operation. So what would this actually look like? Well, so it would basically be combining these two DFAs into a single DFA, which means that it would still accept the language by either A1 or A2, so it would still be valid for any input that we could feed in, either or. So the steps that we want to do to go about doing this is we want to first take the cross product of all the states. So what that means is, for A1, it's the set of Q0 and Q1, and A2 is the set P0, P1. So if we were to cross product this, let's just create some DFA M. The possible states in DFA M, which would be denoted by Q, would be, we would have the pair Q0, P0. We would have Q0, P1, Q1, P0, and we would have Q1, P1, right? So these are all the possible combinations of states that we could have for these two DFAs. So with that being said, we would build this parent DFA, and we can easily see where the transitions are going to go. So if we had, it's obviously going to be 4 states. If we start with 4 states total, we're going to end with 4 states total. So we have 4 states. So our first state here is Q0, P0. So let's go ahead and put Q0, P0. Well, this is going to be our start state because it contains Q0 here and P0. So we know that we're going to start at both of these. So to be able to track this, we can just look at the DFA. We know that Q0 on 0 stays in Q0, and we know P0 on 0 goes to P1. So that would yield Q0, P1. If we go back to our possible states, we see that there's a Q0, P1 right here. So if we feed in 0, transition 0, it's going to go to Q0, P1. Okay? So likewise, from Q0 P1, if we're in Q0 and we feed in a 1, it's going to go to Q1. If we're in P1 and we feed it in a 1, it's going to go to P1. So we have Q1 P1, which is right here. So we know that on a 1, this would go to Q1 P1. So you're starting to get the idea, right? There's all these different transitions that they can take based on the initial DFA that was described above. So we'll have a transition of 0 up here, go down on 0, go over on 1, go up on 0. So this would be our final DFA. The only thing that we're missing are the final states. And what I said before, the final states are going to be any of the final states, because we're unioning, it's any of the final states in A1 or any of the final states in A2, which in this case would be Q0 and P1. So all of the final states in this A1 union A2 DFA would be any of the states containing Q0 or P1. So Q0 is here, so this would be a final state. P1 is here and Q0, so this is a final state. P1 is here, so this is a final state. But Q1 and P0 are not final states in these original DFAs, so this is not a final state. So right here, this is the final DFA. We are now done. This is the final accepting DFA. So what we say is we say that M recognizes A1 union A2. So M recognizes A1 union A2. And this is the proof. So we're done. One thing that I do want to say is that say that we accidentally did this wrong. Say, oh, we were supposed to do this with concatenation, right? You would think that we would need to erase everything. We would need to redo the DFA. But that's actually not true, because the only difference between union and concatenation are going to be the final states. Okay, so this final DFA is going to remain the same, but the difference is the only final states that we're going to accept are the states where Q0 and P1 both exist in the state. So right here, this is the only case that this would happen. So this would be the only final state if we were to do concatenation. Everything else would remain the same. And that is because, like I said just now, because this is a final state and this is a final state, and for concatenation to be true, both of these nodes need to exist within the set. So this is going to be the only final state. So hopefully this was clear to you, and that's pretty much what I wanted to convey in terms of proving the regular operations are closed under union and concatenation. One thing before we go, I just wanted to do one last practice problem, and it's going to be pretty basic, but I just wanted to go through the idea. It's basically something that you can work out. I'll write the solutions within this video, but it's just a basic DFA problem that will probably help you understand some of these basic topics a little bit more. So what I'm going to do is I'm going to construct a DFA M, and we're going to have a state Q1, Q2, and Q3, and Q4. So a DFA is going to have a transition 0, 0, 0, 1, 1, 0, 1. Okay, so the question that I want to ask is, what is the 5-tuple representation of this DFA? So we know that for a DFA, there's always a 5-tuple representation. And that 5-tuple representation is Q sigma Q sigma delta Q naught, and a final state, right? So the question is, how can we break this down? Describe to me what Q sigma, delta, Q0, and F are going to be. So I recommend you pause this video, but I will walk through the example. So we know that Q is the set of states. So here we denote the set by these curly braces. So we're going to say Q is the set of states containing Q1, Q2, Q3, and Q4. So this is what Q is. Next, we want to talk about sigma. So sigma is the input alphabet that is recognized by this DFA. As you see here, we only use 1 and 0s. This is a very common input alphabet. So in this case, the input alphabet are the symbols 0 and 1 that this DFA will recognize. Next, we have the transition function, which is the way that we traverse from state to state. So what I like to do sometimes is create a table. So I have the input character sigma on top, and I have the different states on the sides here. So I have Q1, Q2, Q3, Q4. Right? So what I want to do is to see where I go on each input, what state am I going to end up at? So here I know that on a 0 I go to Q2, Q1, Q1, Q3, Q2, Q4, Q4, and Q4. So this is my transition table. Typically we like to denote the accepting states by circling it or starring it in the table. Just to reemphasize, as an example, mathematically you denote this as delta of Q1. So if you're at state Q1 and you read in a 0, you're going to end up at state Q2. So this right here is representing what this first thing says. So we're in Q1, we read in a 0, we end up at Q2. That's this mathematical notation. Next we have Q0, which is the start states. We know that we start at Q1, so we just put Q1 there. And then F is going to be the set of final states. In this example, we only have one final state, so we just write the set Q4. So this is the set of final states right here. If Q3 was double circled, then we would have the set Q3 comma Q4. So this is again the 5-tuple DFA breakdown that describes this DFA M. One last thing that I want to ask, the last question in this video, just to make sure that you understand how DFAs work, is what is the language that this DFA recognizes? This DFA takes in some 1s, it takes in some 0s, but the ultimate goal is to get to this final state. And I want to know, how do I get to this final state? What series of characters am I going to read that allows me to get here? Well, what you say is M is going to recognize the language. It's going to be a set, and we'll say there's a string W. And here, W is going to be anything that contains the substring 0, 1, 1. And this is supposed to be a 0 right here. Or actually, this is supposed to be a 1. So anytime it reads 0, 1, 1, if that substring exists within the string, then it's going to be accepted. So we can say W contains the substring 0, 1, 1. Okay, so as an example, if we had the string, we fed this in, we read in 1, 1, 1, 0, 1, 0, 1, 1, 0. Okay, well, we already know that the substring right here, 0, 1, 1, so this should actually be accepting, but let's go ahead and test it. If we feed in a 1, it loops back on Q1, so we loop back, we loop back, we loop back, and then we have a 0. So we read in a 0, and it goes to Q2. We read in a 1, it goes to Q3. But then we read in a 0, it's going to jump back to Q2. So we're actually going backwards in the DFA. But then we read in a 1 again. And then we read in a 1 again. And now we're accepting. We're in the accept state. So anything that we put after this accept state is just going to loop back on itself. So it's going to be infinitely accepting. So this is actually an accepting string. But if we were to put in something like 0, 0, 1, 0, this would not be accepting because it doesn't contain this substring 0, 1, 1. So if I put in 0, 0, we come back to Q1, and then I put in a 1 again, and then I read in my final character 0, I'm stuck at Q2. Q2 is not accepting. The only accepting state is Q4, so this is not an accepting string by this language or by this DFA. So that concludes my video on proving that DFAs are closed under the regular operations, as well as giving some examples for the union of two DFAs, as well as another practice problem with the 5-tuple representation for deterministic finite automatas. So thank you guys for watching. If you have any questions, please leave them in the description of this video.